internal flows. So where are we with internal flows? So what we saw so far is that in internal flows, like is the case of a flow inside a pipe in a heat exchanger, we have two things to worry about. One is entry length versus developed flow, and entry length is the distance over which the boundary layers that are generated on the edges of the tube, they eventually collide with each other. Before they collide is the entry length. After they collide, it's the fully developed flow. So entry length, and entry length, we have two things, whether it's the hydrodynamic entry length, that is when the two viscous boundary layers collide, or the thermal entry length, that is when the two thermal boundary layers collide. Depending on the Prandtl number, we're going to have different entry lengths. For the case of Prandtl number equals 1, the Reynolds analogy says both entry lengths are going to be the same, and when both entry lengths, both boundary layers are being developed, is what they call combined entry length, right? And it's, for example, the case of air that has a Prandtl number of 0.7, more or less 1. For the case of oils, the hydrodynamic entry length is very short, and the thermal entry length is long, right? And that's what they call the problem of thermal entry length, and it is for high Prandtl numbers. And for molten metals, we would have the opposite case, in which the thermal entry length is short, and the hydrodynamic entry length is longer. In addition to that, we have to keep in mind whether the fluid is laminar or turbulent. And in pipes, the criterion for turbulent is going to be when the critical Reynolds number is reached. The critical Reynolds number is 2300, and is calculated based on the diameter, not on the length. This is a significant difference with flow in external flows. For example, flow over a plate, the Reynolds number was calculated using a Reynolds number based on distance from the leading edge. So we had the formulas for entry length for laminar flow and turbulent flow. We did well with those, and we discuss also the energy balance in the tube, in which we came to the conclusion that when we're doing calculations in which we use the convection coefficient, when we want to calculate an average, an overall heat transfer over a length of a tube, because the temperature difference between the tube and the fluid is changing constantly, we need to use the delta T log mean that was expressed, delta T log mean that has this expression here. What else? We also saw that that depending whether the pipe had a constant heat flux or constant surface temperature, we had different types, different cases in the heating of the fluid. When we have a constant heat flux, the temperature of the fluid keeps, for example, if we are constantly heating the fluid with a constant heat flux, the temperature of the fluid keeps increasing and increasing and increasing. And all this came from the analysis of the energy balance in the tube, which we did in week 4 in differential control volumes. We also said that the convection coefficient, the local convection coefficient, was high near the entry of the tube, because it's the entry length, and then it gets to a constant value. And for that reason, we would have inside the tube, let's use the pointer here. Inside the tube, we would have high convection coefficient at the entry. It gets down until it gets a steady state value at the at the entry length, at the thermal entry length, and then it gets constant. So if we have a constant heat input into the tube, we know that the temperature difference between the surface of the tube and the fluid is going to be associated with this heat flux and the convection coefficient, such that, and here we have this expression: heat flux heat flux matches the convection coefficient and the temperature jump. So when the convection coefficient is high, the temperature jump would be small. And this is what we see in the entry length of a pipe that is being heated, that at the beginning, the surface temperature of the pipe is pretty much the same as that of the fluid because of these, because the high convection coefficient. And once it reaches the entry length and the fluid is fully developed thermally, there is going to be a temperature gradient that is constant through the length of the tube. We also saw the case in which the tube has a constant surface temperature. And if it has a constant surface temperature, the temperature difference between the tube and the fluid is going to be changing constantly. And as we discussed before, it is in this case in which we use the concept of delta T log mean. In this case, we also see, in the case of a constant tube temperature, what we see is that that as the fluid goes down the pipe, the temperature difference between fluid and pipe gets reduced to be essentially zero, and we would have no heat transfer here. We pay the same money for a piece of tube in this region of the heat exchanger than for this other region of the heat exchanger. So the heat exchanger is going to increase in cost proportionally with the length of the tubes, but the heat transfer does not increase proportionally with the length of the tubes. It's much better to have double the tubes that are short than half the tubes that are very long and eventually get into thermal equilibrium with very poor heat transfer. In this class, we're discussing the fundamentals and understanding what's happening with heat transfer. When you're in your design class, especially those of you in chemical engineering, you will be using all these concepts as you design heat exchangers and design plants and select components for a chemical plant. Okay, so what I would like to do today is to discuss the origin of the correlations for convection coefficient in tubes and see a few different correlations out there in addition to understand it, to see what is out there and to do an example. So let's see. Here we have a schematic of a tube in which we have the tube is heating up the fluid and the fluid is moving, let's say, left to right. On the next to the surface of the tube, the fluid is hot and is at the temperature of the tube. And at the center, it has a lower temperature because it's the fluid that is getting heated up. And heat comes in by conduction, right? Remember that convection, there's no such thing. In reality, there's conduction and advection. Both together is what we call convection. So the heat comes as the fluid moves down and transfers heat by advection. The heat that comes into the fluid comes in by conduction. And if this is a temperature profile of in the fluid, we know that the gradient of this temperature profile is what, according to Fourier's law, is what gives us the heat transfer by conduction. So in this case, we would have, here is Ts, is the temperature at the surface of the pipe. This is T minimum. And this, in here, this dashed line is the mean temperature, right? We have used this concept without mentioning it before, because when we talked about heat transfer in by advection in a tube of a heat exchanger, we were always talking about mean temperature, but we had never been explicit. Now that we're looking into the details, we are saying, okay, let's pay attention to what we used to call just temperature. In reality, is a surface temperature, is a minimum temperature, is a mean temperature. There are many things we must keep track of. And so in this case, we would say the Q, that the heat that comes in by convection, has this formula that is a definition that says is H T surface of the pipe, right? This temperature at this surface, minus the mean temperature, right? This is the way, this is the difference we used to define the convection coefficient inside the tube. If you remember, we already discussed this. In external flows, we use the temperature of the fluid far away, right? Yeah, it would be T infinity. But inside in internal flows, we don't have a T infinity because there is no such thing as infinity. There is the other side of the pipe or whatever the internal flow is. So in that case, we consider convection as the temperature difference between the surface and the average, the mean temperature. Okay, so this definition of heat by convection, we know in reality is heat by conduction, right? Now we don't have a boundary layer anymore when it's fully developed flow. The two boundary layers collapse, and we have a temperature profile that is established and is maintained inside the pipe. And this heat by conduction is K dt dr, which this is Fourier's law. Here I'm going to make an approximation just for us to be more or less on the ballpark. And instead of dt dr, we're going to say surface temperature minus, this is a maximum temperature minus minimum, right? T surface minus T minimum over this radius, right? This is a very rough approximation over this radius. And this T surface minus T minimum, right, is more or less, and this is again approximating, T surface minus T minimum is more or less twice this other difference between T surface and the mean temperature. So that's why this number 2 appears here. We have 2 times the difference between the surface and the mean. If you look at this equation here, we said H delta T equals K times 2 delta T over radius, right? So I can forget about the delta T's in here and in there, and we would have then H equals 2K over radius or 4K over diameter. Whatever, that sounds like a kind of an interesting result in itself, but cute, but nothing more. But when we define the Nusselt number, right, because we tabulate convection coefficients as Nusselt numbers, the book does not have a list of convection coefficients. The book has a list of Nusselt numbers from which we can calculate a convection coefficient. And they do this not to torture anybody, but just to have like enormous amount of generality, that tabulating things as Nusselt based on Reynolds and Prandtl, they can do this for any fluid and any size, as long as we match the limitations of the correlations they have. So, so we have Nusselt that is hd over k, right? Is hd over k. If I look at this, we're going to get that Nusselt is more or less 4 in a pipe, right? We did this simple analysis. If you look at the book, you can knock yourself over with equation after equation. And I love those equations, but you know what? It's more or less 4, give or take. And we didn't need to make any big equations here. It's just a little bit of thinking. But if you do the equations, and if you invest 4 years of your life in a PhD, or you lose 4 years of your life in a PhD, you're going to end up that it's not really 4, depending on the boundary condition. For the condition of constant surface flux, is 4.36. We were off by less than 10%, but 4.36. And if it is a pipe at constant surface temperature, we would have a Nusselt of 3.66. Again, less than 10% error. So this story I told you here is just an approximation to make sense. These are the numbers we're going to be using when we make calculations in life or calculations in an exam. The book does explain where these numbers come from. And after 3 pages of equations, I think you'll be happy to have just one line in which you get the gist of what's going on. We can do better than that. But we got a 4 more or less right, fairly easy. The other 10%, I'm going to leave it to mathematicians. So another interesting thing, see that we have 2 different correlations depending on whether we have a constant heat flux or a constant surface temperature. If we were in person in the class right now, I would ask you, do you remember last time you saw something like that? But I'm not seeing you. So I'm going to tell you, because it would be awesome to get into this together. Do you remember when we did the semi-infinite solid? When we did the semi-infinite solid, we came to the conclusion that for the constant surface temperature, we would have a coefficient that was square root of pi, more or less 1.77 square root of alpha t for the heat penetration. And for the case of constant heat flux was 1.15, right? And those 2 numbers are not the same, but are quite similar. We said, well, as a ballpark, we could say 1.5, right? And we see the same story repeating here again. We have 2 numbers that are quite similar. The boundary conditions are different, but the transport of heat by heat thermal diffusion is very similar. So this number 4 is something good to keep in mind, to remember, but we know the exact numbers would be 4.36 or 3.66. So similar, right? When we have a temperature dependent fluid, we would have a whole gradient of temperatures inside the pipe. At what temperature do you pick the properties? And you pick the properties, people have agree on this, to pick the properties at the mean temperature. So at a given point in the pipe. So now that we have seen this, let's go to see some correlations, and then we can do some problem. Let's see. Okay. So let's talk about we just talked about laminar flow, right? We talked about laminar flow, and we said Nusselt is more or less 4, period. In laminar flow, that's it. In turbulent flow, now I cannot do any other kind of smart derivation because I ran out of smarts, or things became very empirical. So this condition, and it's so common to have turbulent flows inside of pipes that people have investigated it, and this correlation even has a name, Ditus-Belter equation. And it's a very simple thing. It says that the Nusselt number, right, in turbulent flow, the Nusselt, and this is once the fluid is turbulent, this is constant. A constant value of Nusselt is this coefficient 0.023 times Reynolds to the 4/5 times Prandtl to the n. Check this out, and this is the reason I spent so much time going over boundary layers in the flat plate. For turbulent flow, the Nusselt is proportional to Reynolds to the 4/5, 0.8. That is the same exponent of Reynolds we had in the flat plate. A tube and an airplane wing don't look the same at all. But from the point of view of heat transfer, there is so much that is true that is true for both. And the heat transfer by turbulence being Reynolds to the 0.8 seems to be quite universal. I cannot give you a law of why it is that universal, but I'm just bringing your attention to it because it appears all the time. And Prandtl to the n. Oh, what n might be? Okay, let's see. Oh, 0.4 or 0.3, depending on whether it's heating or cooling. Isn't this all too similar to the 0.33, right? We're bracketing the 0.33 that came from the external for the heat transfer over a turbulent heat transfer over a flat plate in a turbulent situation. So much the same. Isn't this amazing? The only thing that changed between pipes and a flat plate is that this coefficient here. Both exponents here are pretty much the same. Now, this Ditus-Belter equation is for small temperature differences between the pipe and the fluid. From the point of view of heat transfer, that's not such a big deal, but from a point of view of fluid flow, when the temperature difference is big, the viscosity changes a lot, right? And when the viscosity changes a lot, the Prandtl number changes a lot because Prandtl is a ratio of viscosity to thermal conductivity, right? Of kinematic viscosity to thermal diffusivity. So people said, okay, let's go one more turn of the screw here. And when the difference is large, they accommodate by having an equation that looks so much the same as before, but now we have a ratio of viscosities where mu is the viscosity at the mean temperature, and mu s is a viscosity at the surface temperature, at the temperature of the pipe. So now we can account for large temperature variations and large variations in viscosity. Raised to an exponent of 0.14. This is empirical. This just works. The same as the 0.4 and the 0.3 before. Those were empirical. They just worked. It's just a coincidence it's so similar to the 1/3. And here, guess what? They said, screw it, 1/3. Here I have my 1/3. This formula here is almost exactly the same as a flat plate. Only the coefficient here has changed. And with this, we account for temperature differences. From the point of view of plug and chug, you just look at this and you plug and you chug. Easy. But from the point of view of relating things and making sense, we know what this Prandtl to 1/3 is doing. We know that this is not good for molten metals because molten metals has something else, right? We know that this is for turbulent because it's a Reynolds to the 4/5 instead of being Reynolds to the 1/2 or something like that. That is the common exponent. And this number here that doesn't have a physical meaning. This just comes from the correlations, and these are tabulated. In this case, it's just part of the formula. This is the way we're taking apart all these formulas that are just given to us without much explanation. For the entry region, there are correlations too for heat transfer in the entry region. And we have these curves, and these are complex to read, and the associated formulas, which we're gonna do one of these as an example, they're painful just even to look at, right? But remember, every time you see a formula like 8.58, and you say, I don't even want to look at this formula, just think that before you had felt the pain of reading it, somebody had the pain of writing it. And to write it, somebody had to be measuring a whole lot of tubes. And you're so happy that somebody's not you. Although some of you might choose to do a PhD. This is a type of thing that would be coming out of your PhD. And you'll be so proud of it, right? And then other people would use it. And hopefully some people say thanks. All right, so what are these curves here? We have Nusselt, and you see this is a local Nusselt, it's just Nusselt. And this one with the bar is average Nusselt. And this is in the laminar entry. The horizontal axis here, this is a dimensionless group called the Kretz number, and I'm not gonna get too excited about it because the physical meaning of it is like it's essentially a dimensionless length from the entrance downstream, right? And here you have you have an expression of how to calculate it, or we have it here. But that doesn't matter. So here we have this Kretz is a 1/Kretz number, right? That the dimensionless length from the entry, from the inlet. And what do we see? A high Nusselt, right? Next to the inlet, you have a high Nusselt. We already discussed because the boundary layer is thin. And this high convex Nusselt number comes down to, guess what? To something more or less like 4. This more or less like 4 area is the area where we have fully developed flow. Now, depending on the boundary condition, whether it's a tube with constant surface heat flux or constant surface temperature, was a little bit more than 4 or a little bit less than 4. But it's more or less 4, as we already saw and we knew. And the fact that the Nusselt number goes up is something we also knew and we expected. Now we have the numbers with which to calculate it. Now, what is the difference between the dashed line and the red line, and the solid line? Let's start with the solid line. Solid lines are the case in which they talk about combined entry length, and you see that it says Prandtl 0.7. It's not that 0.7 is anything especially interesting. It's that 0.7 is air and most gases. So every time you see Prandtl equals 0.7, that says I'm talking about air. So and because it's so close to 1, we're pretty much in the Reynolds analogy. So both entry lengths are the same. And we have this number here. You see this dashed line now? This dashed line now is a lower, corresponds to lower Nusselt numbers. This is the case in which the hydrodynamic entry length was very short and the thermal entry length was long. This is the case of oil and water too, right? So for air, we have the Reynolds analogy. We would have this heat transfer at the entry length. And for oil and water that are very viscous, we have this other different, slightly lower Nusselt number for entry length. This curve on the right, now they are for average. So in theory, from one of these, you can derive this other one, right? Average, this is average Nusselt for entry length for constant temperature, right? Constant surface pipe surface temperature. So, and we have two cases. The case here for equation 8.58, you see the circles. These are for Prandtl. This is the Reynolds analogy, and perhaps even lower values, right? 1 and slightly less than 1. You see these triangles here? This is Prandtl 5, right? Water is a Prandtl of 7, right? So this is viscous fluids here, and this is the air that has same entry lengths, same thermal and hydrodynamic entry lengths are the same. So we have these two formulas here. One is simple, the other is more complex. This formula covers, this formula here, right, covers, is included in this other one, right? But if you have a Prandtl more or less bigger than 5, which is the case of water, I'll be happy to take on this formula. If you have something that the Prandtl is less than 5, like the case of air, this is the other formula you would be using. And what do we need to calculate this formula? See, the Kretz number. That's the only input we need. So we need to calculate the Kretz number to use this formula. And the Kretz number depends on Reynolds, which we know how to calculate, Prandtl, and we have d over x. D is the diameter of the pipe, and x is the length we're talking about. So the average is the average between entry and whatever length x we are talking about. Okay, and you get to see that when the length is very, very large, right, Kretz number tends to 0. And when Kretz number tends to 0, guess what? The Nusselt tends to 3.66. That's not a surprise to anybody. 3.66. That is the Nusselt number for a pipe in laminar flow and constant surface temperature, right? And this is what this formula is for, Ts constant. Anyway, now we know how to calculate. A Nusselt, to calculate the convection coefficient in a pipe, like in a heat exchanger, we need the Nusselt. And the Nusselt is, if it is a laminar flow is more or less 4, right? Depending on the boundary condition, a little bit more than 4, a little bit less than 4. If it is turbulent, we have formulas. We have this Dietz-Pelter equation that looks so much like a flat plate. And all we need to do is calculate Reynolds, and we know the Prandtl, and we're awesome. If we are talking about the entry region, we can also calculate it, right? This is the laminar entry region. And this formula reduces to the case of the laminar flow in fully developed region. For turbulent entry region, we also have formulas. Now, the book has cheated us here. For a short tube, the turbulent entry region, we have this formula that depends on constant C and M. And you know what? The book didn't put what it is. So if you ever need to do it, the book has a reference, and you have to go to that original paper and get a table of C and M. And for long tubes, when the tube is has more than, the length of the tube is more than 60 diameters, the average Nusselt is essentially the Nusselt for fully developed flow, right? And because this is turbulent, we're talking about this Nusselt for fully developed, we're talking about this one here. The Dietz-Pelter equation, or this other equation that is an upgrade over that. How about turbulent molten metals? Well, for turbulent molten metals, what we have is equations that are interesting, are somewhat similar, have a small twist. Here we have Nusselt is a formula that depends on the Peclet number. Now, we already discussed what the Peclet number is. It's the ratio of advection to conduction. But if we remember that Peclet number is by definition the same as Reynolds times Prandtl, we see that in this formula, we have a coefficient times Reynolds to the 0.8. And guess what? Turbulent flow, Reynolds to the 0.8. And then we have Prandtl also to the 0.8. Do you remember that for the flat plate, the boundary layer, in the case of molten metals, right, was Reynolds to the 1/2, Prandtl to the 1/2. Both went together. And in this case, we see the same, that the Reynolds and Prandtl would have the same exponent, 0.8. So interesting. Now, there is something that is different. That is this factor of 4.82 here, this term, right? That is a constant term. We don't have that constant term, for example, in the case of fully developed flow, of turbulent flow in things that are like, that have high Prandtl numbers. I'm myself not sure why we have this term, but let me tell you what I suspect happened here. When, as the Prandtl number, as the fluid flow is smaller and smaller, right? We would have a smaller Reynolds and a smaller Prandtl. So the heat transfer would be lower. However, we're talking about turbulent molten metals in which conduction still matters. So these constant factors here, I believe they're just empirical, but they're empirical capturing the fact that even when the fluid flow is smaller, conduction, when the fluid flow is smaller, conduction starts to become more and more relevant. And we have some amount of heat transfer that is more what we would have if we were transporting oil. Because if oil is not moving, it's really not transporting heat. But if a metal is not moving, it's still transporting quite a bit of heat by conduction. That's what I think is going on in these formulas. In any case, this conversation is, so you have a sense where it comes from. In the end, all we do is plug and chug, get a Nusselt number, and from Nusselt, we get a convection coefficient H. So we have a few more minutes, and I'd like to start a problem to look at these things in concrete. So let's do this calculation example here. So this is a straightforward problem. Calculate the convection coefficient for fully developed flow in a tube of 1 inch inner diameter, transporting 25 cubic centimeters per second of water at room temperature. Also calculate the hydrodynamic and thermal entry lengths of this tube. I know for a fact that you know how to calculate a hydrodynamic entry length very well, because you did it on Monday. Assume constant tube surface temperature. And here we have the thermophysical properties of water, that these are approximate, but more or less easy to remember. So this is a standard problem. They don't tell us if the fluid is laminar or turbulent. So what formula do we use? Well, first of all, we have to determine if it is laminar or turbulent. So for these steps are the same steps that we follow for external convection, right? Number one, determine Reynolds number and Prandtl and all those things. So how do we determine the Reynolds number? Reynolds number is mean velocity times diameter over kinematic viscosity. Fine, what is the mean velocity? Because they didn't give us mean velocity, they gave us the volumetric rate. Okay, mean velocity is by definition is the volumetric flow divided the cross-sectional area, right? And the volumetric flow is if we were given the flow in mass instead of cubic meters per second, we would relate the mass flow divided by the density. In any case, let's do this calculation here. We have volumetric flow, 25 cubic centimeters per second, good. Cross-sectional area, pi diameter square over 4, and we get the value for the cross-sectional area. Applying this formula, we get a mean velocity of almost 5 centimeters per second, right? Reasonable numbers. Okay, so now that we have the mean velocity, we can calculate the Reynolds number. For the Reynolds number, we need kinematic viscosity, but we have the diffusivity and Prandtl. And I know you know how to do this as of Monday. So we have kinematic viscosity is thermal diffusivity times Prandtl, and it gives us this 1.05 times 10 to the minus 6 meters squared per second. Yeah, kinematic, quite reasonable again. Now we can calculate the Reynolds, and it gives us a Reynolds of 1194. So this Reynolds that is almost 1200 is less than the 2300 that is the criterion we're using in this class to determine whether the flow is laminar or turbulent. So for sure, this at 20, if you remember what I said at 2300, the flow started to transition. So anything above, if we had a value slightly above 2300, might not be fully turbulent, but might be in transition. But if the number is below 2300, that's laminar for sure. So laminar flow. So now I know we're talking about a piping laminar flow, and they tell us it's fully developed. So we know we don't need to worry about entry length. We don't need to worry about Kreiz number or anything like that. And let's get the Nusselt number then. For the Nusselt number, we had two options. No, it's for the Nusselt number, we had, it said constant surface temperature, right? And we had seen that for constant surface temperature is 3.60, Nusselt is 3.66. That's just a number. Look how easy. No Reynolds, no Prandtl, no nothing. This is what it is. So we go here. By the way, in this table, which we'll discuss later, it tells us for a pipe of circular cross-section, depending on if it is uniform heat or uniform temperature, constant surface temperature is 3.66. And we put it here, 3.66. So I unpack the Nusselt number to calculate H, right? And as you have already done, and you know this, so H is Nusselt times thermal conductivity over the pipe diameter, and it gives us an 86.46, 86 and a half watts per meter square Kelvin. This is water inside the tube, right? And yeah, it's if we had invented a number, we would have called it 1,000 because it's forced flow of water. But inside the pipes, what happens is eventually the flow gets fully developed and the heat transfer gets locked. It cannot get any better, right? So it's good to know, and this would be the exact value to use. And by the way, if you're designing a heat exchanger, this value would be very much what you measure, right? This is a real correlation giving you real values. And also shows us the limitations of the things we used to assume just because they were easy to memorize, right? There can be some error in some of those. Okay, they asked us the calculation of thermal entry length, but you already looked at entry length for the quiz, and you did awesome on that. And yeah, you would calculate 0.05 Reynolds for hydrodynamic entry length, and 0.05 Reynolds times Prandtl for the thermal entry length. And what we get? The thermal entry length would be 10.5 meters thermally, and because water is much more viscous than is conductive, as shown by the Prandtl number of 7, tells us that it would be fully developed hydrodynamically after 1.5 meters, right? In this pipe, the first 1.5 meters are just, it's a hydrodynamic boundary layer that is developing. And for 1.5 meters, these two boundary layers don't collide. And the heat transfer here is enhanced. And thermally, the heat actually takes even longer to have the two boundary layers collide. It takes 10 meters. So if this pipe is less than 10 meters long, actually the heat transfer coefficient is going to be higher than what that this correlation indicates of 3.66, because 3.66 is for fully developed flow. But if the pipe is less than 10 meters, we don't have a fully developed thermal flow, thermal regime. Okay, it's just 1:51, so we're gonna stop here and we're gonna wrap up internal flows on Friday. Please, if you have a chance, participate in the anonymous survey I put. I would love to hear your feedback about quiz 3 and see how much I can implement in the last stage of the class. Thank you. I'll see you on Friday.